So today we're going to be doing the mechanism for glycoside formation. Before we start with the mechanism, I just want to go over some brief rules/tips that might help you so you don't miss any points on your exam. The first one is that you always want to start your arrow from an area that has electrons or has an excess of electrons to an area that is deficient on electrons or lacks electrons. So an example right here, we have an ethoxide ion. The oxygen has a negative charge on it, and so we would want to draw our arrow pushing from the oxygen to the partial positive of the carbonyl compound. We never want to do the opposite way because there's no electrons to move. And the second one is to show your equilibrium arrows when necessary. So if you've got two reactants that are equilibrium with each other, meaning they're reversible, you want to show those arrows. If it's a one-step or one-way reaction, you want to make sure that you show the one-way reaction arrow. So we're going to be doing the mechanism for the glycoside formation, and we're going to be starting with the sugar. The sugar is a beta-D-glucose, and we're going to be treating it with hydrochloric acid and a alcohol, and the result will be a acetyl that is formed. And so let's start with the mechanism. So the first step of the reaction is to identify, or for any mechanism, is to identify what's changing from your products and your starting material. So if we look at the two rings really quickly, we can see that the two things that we are changing is going to be on this anomeric carbon. This OH is going to become an OCH2CH3. And all the other carbons have retained their stereochemistry and their substituents, so the reaction or the mechanism isn't going to be happening with those groups. So the first step is to create a good leaving group. We replace the OH with the OCH2CH3. And so what we want to do is get rid of the OH somehow. Hopefully you remember from your earlier OChem that OH is a really bad leaving group. And so in order to make it a good leaving group, we're going to take use of this acid, or the hydrochloric acid, that is present. And so the electrons on the oxygen will pick up a proton, and so that will result in a structure that puts a positive charge on the oxygen, and that positive charge makes it a good leaving group. And so if I draw this really quickly, we've protonated the hydroxyl group that is on the anomeric carbon, and the result is an OH2+. And so if this leaving group were to leave, it would come off as H2O. Now that carbon is just not going to let OH2 come off, because it would leave a positive charge on that carbon. And so the result would be that we need to somehow replace a bond with that carbon that would force OH2+ to come off as H2O. And so what's going to force the OH2+ to come off is the oxygen that is adjacent to the carbonyl, or the anomeric carbon. And so it's going to drop its electron density down, forming a double bond. And that's going to push off the OH2+, coming off as water. And so we end up with an intermediate that puts a positive charge on that oxygen. And so this particular form, or this structure, is called an oxocarbenium. And you don't need to know that vocab for the exam, but just in case you wanted to know what that structure was called, the double bonded oxygen with a positive charge is called the oxocarbenium. And so the next step is to attach or figure out where this OCH2CH3 is going to come into play. We have an alcohol that's present, and so that alcohol has the OCH2CH3, and so it's going to attack something that has a positive charge, or a partial positive. And so if we were to do resonance structures for this structure right here, we would realize that we would have a positive charge on the carbon and a neutral charge on the oxygen. And so the electron density on this alcohol right here will come in and attack that position, pushing these electrons on top. And so the structure we're left with now is going to be a positive charge on the oxygen. And so we're almost close to our final product. There's one last step we need to do. The oxygen is lacking electrons, and because there's a hydrogen attached to it, that hydrogen is very acidic. So we're going to have a base come in, remove the hydrogen, and it's going to restore those electrons back onto oxygen, resulting in a neutral structure. The base we will be using could be Cl-, so I'll draw that in. And this comes from the acid, initially from HCl. And so oxygen gets its neutral charge back. We reform our HCl, hence why we only need a catalytic amount, and we're left with our product. So two things to note: this entire reaction or mechanism is reversible. So we can start with the OH and go to the OH-CH2CH3, or we could also go in reverse. If you need some more practice doing this problem, I would suggest doing the reaction in reverse and doing the arrow pushing.